All right, and next we're going to have James Mang talking about models for substellar objects in chemical disequilibrium with water and ammonia clouds. So please take it away.
Thank you. Hi, everyone. My name is James Mang. I'm a third-year grad student at UT Austin, working with Caroline Morley. And today I'll be talking about our ongoing modeling efforts for these ultra-cool substellar worlds and the next grid of Sonora, atmospheric, and evolution models that will probe down to Neptune-like temperatures. Because JWST is now, I'm making fancy slides here. Because JWST is now enabling us to directly observe the atmospheres of not only white dwarfs at extremely high precision, but also temperate giant planets. Now, brown dwarfs have been the perfect analog for us to study thus far. They share the effective temperatures and masses as these gas giant planets, and therefore will have similar atmospheric chemistry. If we look at this color magnitude diagram, we can see that directly imaged exoplanets in the bolded circles, and this is from Bowler 2016, and they live in the same regime and areas at which these brown dwarfs are. As you've seen and heard so far from the session, we are still learning a lot from these cold brown dwarfs and these objects here, but the extent of our capabilities don't stop at wide dwarfs anymore, and we're extending towards colder objects and true Jupiter analogs. And we can go even colder with JWST, and so we're preparing for cold programs at these true Jupiter analogs, while we continue to try and fit these current wide dwarf atmospheric models. And so to do this, we need to go to colder temperatures, and that will be probing Jupiter and Saturn-like temperatures down to even Neptune-like temperatures at 75 Kelvin. Include clouds for these atmospheres, because we know water and ammonia clouds should be present in the atmospheres when we look at gas giants in our own solar system. And include more chemically dynamic and chemical disequilibrium, for example, because we can see that there should be strong vertical mixing present in the atmospheres of these objects. And one of our favorite wide dwarfs is the Coldest, WISE 0855, which is about 250 Kelvin. It's in that perfect range where it's cold enough for water clouds to condense, but warm enough so ammonia clouds don't form. And so this is providing us a direct observation of potential water cloud features on an extrasolar object. And you can learn more about the JWST program that we're working on to study WISE 855 from Brittany Miles on Friday. And there are a few other programs studying wide dwarfs that we mentioned earlier today as well, and that are being done with JWST. And now we have the actual capability to actually do similar studies on true Jupiter analogs, and even sub-Saturns that are even colder than WISE 855. So for some of these temperate giant planets, different types of clouds are expected to form, and it's going to affect the spectral features of these objects. And so here I'm showing a selection of RV detected temperate giant planets, where I'm showing the mass on the y-axis and effective temperature on the x-axis, adapted from Lupi et al. 2016. And so here you can see at different temperature ranges, there's going to be alkali, water, ammonia, and methane clouds that could potentially form on these objects. And JWST has actually started to observe some of these planets, like Epsilon Area B, 14 Herc, and there's all these other programs that are planned or ongoing with JWST to actually observe and possibly detect sub-Saturns, even Neptune-sized planets around M dwarfs. And so one example of a current JWST program is Epsilon Indi AB. And so here are JWST images of Epsilon Indi AB at around 10 and 15 micron. It is estimated to be at around 280 Kelvin and approximately 6 Jupiter masses from this observation. And this is just one of many temperate giant planets with more colder Jupiter analogs that will be observed with JWST. There are also several programs now using JWST to look at and try to confirm planetary candidates around white dwarfs. And so here I'm showing the left here is the IR excess of a planetary candidate. And so you can see at the excess at 18 and 21 microns. And when compared to some models for these cold substellar objects, it's most similar to about a 248 Kelvin object. And this could also be a disk. It cannot be ruled out yet that it could not be a disk around this white dwarf. But there are planned follow-up observation programs with JWST to do this and confirm this. If it is indeed a planetary object, this could be a 3 Jupiter mass planet. But these are model-based derivations. And so therefore, they could vary depending on the models that you're using. And so there are many programs looking at these ultra-cool substellar worlds now with JWST that require a new set of models that can actually probe and suit this parameter space. Because now that we have the technological capability to actually observe this wide range of gas giants, we need to catch up with our models. And so here I'm showing a simulated spectrum of an irradiated locality Jupiter analog with an effective temperature of about 130 Kelvin, and with a supersolar melicity like Jupiter to guide the eye for what features we might see from these objects as we go along. So if we try to fit the spectrum with the latest SNORA models, like SNORA alpha here, which includes chemical disequilibrium, but is cloud-free in this case, it doesn't probe cold enough to match a Jupiter analog that's around 130 Kelvin, because the coldest temperature that this grid goes to is 275 Kelvin. If we go back to the original SNORA PopCat models, they're also cloud-free and only goes down to 200 Kelvin in this case. So there are several other grids of models available, like the ones that Brianna was discussed earlier on, but I'm just showing examples from the SNORA family models here. But in all cases, no grid currently probes down to Neptune-like temperatures. So our new grid is going to probe down to deeper and colder objects. And this also includes super and subsolar melistes and Cedo ratios. As you can see here, a clear atmosphere in chemical equilibrium at the right effect temperature probes closer to the expected Jupiter analog, but it's still missing a couple of key factors. And one of them is clouds. And if we look at the latest evolutions from the SNORA Diamondback models released by Caroline this year for warm L and T dwarfs, which she'll also be talking about more on Friday, we can see that these models are for cloud-free objects in the dashed lines and hybrid models with clouds for objects warmer than 1300 Kelvin, here shown in solid lines. And it goes from hotter and younger ages at the top left corner down to, as we follow the cooling track as a function of time, towards the right. More importantly, as you can see, is the effect of including clouds in these warmer brown dwarfs, showing variations in evolution tracks by a couple hundreds of Kelvin. And these cold objects in evolution models are cloud-free, and so water and ammonia clouds need to be included for these models, and so we can actually probe to actually even lower masses for Saturn and Neptune-like objects as well. If we include the clouds here, we can see that the water and ammonia clouds in the atmosphere really suppresses thermal emission from this spectrum. But here, the cloudy model is too optically thick of a cloud that's been included. And so you can think about some variation of some amounts of fractions of clouds that might be some patchiness included as well, that could actually help better fit something between a cloudy and a clear model. But also another consideration is the chemical treatment of the atmosphere. So here I'm showing the abundances of a set of molecules in the atmosphere in chemical equilibrium, from the top of the atmosphere down to the bottom of the atmosphere. And so in our SNORA family of models, chemical equilibrium has always included rainout chemistry. We can see, for example, the gas abundance of water here falling based on that treatment where we expect water to condense. Now, if the atmosphere was in chemical disequilibrium, these species will have a constant abundance above the quench point, which Brianna explained in detail earlier on. And so with these different quench points is where the mixing time scale is equal to the chemical time scale. And so you can see examples of this, for example, the CO2 quench point here, the carbon monoxide, methane, and water quench point, and the ammonia and N2 quench point here in this case. And this is the treatment that's used in the SNORA alpha set of models, except phosphine is also kept in equilibrium there as well. So in this new set of models, we're going to do disequilibrium chemistry, where we take a hybrid approach, especially because this is the first time we're really getting to the regime, where these condensates are going to have a large effect from these condensating species like water and ammonia when doing disequilibrium chemistry at the same time. And similar to alpha, we will keep this phosphine in equilibrium for now, since we don't really see phosphine gas further up in the atmosphere based on the observations and lessons that we're learning from these programs thus far. But we're also going to include, instead of quenching every species, the rainout chemistry for volatile species like water and ammonia in this case. And so now with this hybrid quenching modeling approach, we can see the comparison between the two disequilibrium chemistry treatments that we see in the spectrum. So here's a spectrum at 130 Kelvin following the same chemical treatment as done in alpha, where all species are held constant above the quench point, except for phosphine that is in chemical equilibrium. So what happens after we quench and allow water and ammonia to actually rain out the atmosphere? Well, we can actually see large differences in the different regions. For example, here, where water is affecting it around 2.5 to 2.8 microns. And for example, the ammonia that we have quenched, that we didn't quench, in this case, around 4.1 to 4.6 microns. And finally, we can also include clouds and get a closer fit to these Jupiter analog that are simulated. As for all complex systems, there will also be intricacies and different knobs you return to better fit the observations and these types of different spectras. But our new grid of model probes wide enough that will provide more direct comparisons for JWST temperate giant planets and the coldest white dwarfs to actually better estimate the physical parameters of these objects. So what parameters are we probing in this grid? We're going to be the coldest models yet down to 75 Kelvin for Neptune-like objects. We're going to do surface gravities, log G's to 3 to 5.5. And it'll be cloud-free and cloudy atmospheres with water and ammonia clouds included, for example, the coldest objects. And it'll be in chemical equilibrium and disequilibrium with a variety of KZZs for the disequilibrium models and using the hybrid approach that I just described. And it will also, of course, cover a large range of mellices and C to O ratios, so it encompasses the gas giant objects that we see, for example, properties in our own solar system. So for all these models, I've been using Picasso. It's an open source Python package that was first used to generate transit spectra along with thermal emission and reflected light spectra. But now includes the capability to actually run atmospheric climate models. And so Picasso climate models includes the capability to run models specifically in chemical disequilibrium. And this was developed by Shannon Mukherjee and used to produce the Sonora alpha owl for these clear substellar atmospheres. And I've been working on Picasso to actually include the clouds to integrate it into the chemical equilibrium and disequilibrium framework to generate this new suite of Sonora models. So you can follow our latest developments on the GitHub by scanning this QR code here. It's publicly available, and you can use the latest code as well with all the intricacies that I've introduced here. But some of the intricacies that I've described haven't been fully rolled out to the main branch of the actual GitHub. And so there's some things that you can actually talk to me about if you want some more customized to play around with these different changes that I've made. So in conclusion, JWST is now enabling us to actually characterize the atmospheres of true Jupiter analogs and even colder than the coldest white dwarfs for the very first time. And therefore, we need these new atmospheric evolution models that better suits the parameter space of our gas giants in mellices, C to O ratios, and temperatures, but also include lessons that we've learned thus far from other brown dwarfs and other JWST programs, like keeping phosphine in equilibrium and with different expected cloud species that might form in these atmospheres. And our Sonora models are going to be released in two sets. The first is going to be for the cloud-free, clear atmospheres for both equilibrium and disequilibrium down to 75 Kelvin, with the second set being for the cloudy atmospheres that includes water and the ammonia clouds as well. And these models would better suit the analysis of JWST observations of, for example, epsilon NDAB, epsilon ARB, 14 Hz, and all the other ultra cool substellar programs that are ongoing with JWST. And with that, I'll stop here and take any questions. Thank you.
Thank you so much. Any questions for the audience? From the audience? Kim, sorry, I didn't see.
Please repeat the question.
Okay.
More Smith College. This is a great talk. Really exciting to see these models coming together. I have two quick questions. One is, what does the ammonia behavior look like in the Q branch when you go out to the mid-infrared? Does it kind of look like what you're seeing in the infrared? And then have you picked a fun new desert animal?
So the first question was asking about what the Q branch looks like if you look further out for the ammonia, for example, in that case. And if we keep it in chemical disequilibrium where it's keeping constant in that case, it will follow the same features that you would see as you expect in the cross sections that you have for ammonia further out. But if you rain it out, of course, in that case, then you won't see it further up in the atmosphere. The second question is which desert animal we're going to name it after. Following the alphabetical order, the next set will start with the letter F for the either flora or fauna, but has not been decided yet. So that's going to be an exciting discussion between all of us.
So are you going to, now that you have both clouds and disequilibrium texture here, are you gonna do different like fixed cases like alpha owl, or are you gonna go back to kind of trying to predict what the mixing should be, so that you don't have to do a full thing?
Yes.
Based on, like,
So the question asking about what treatment of KZZ we're going to be using, whether it's constant or self-consistent modeling in that case. The plan right now is to do constant values following on the Sonora alpha owl models, just because we're going to extend the Sonora alpha owl basically down to 75 Kelvin for the clear atmospheres, essentially from the 275 Kelvin it stopped at, but also including the cloudy and the hybrid model approach for those up to maybe around 450 Kelvin, where we expect the rain out for these species to actually start affecting the chemical disequilibrium treatment that we're talking about. But yeah.
One more quick question, maybe from this side of the audience that I haven't seen much.
Very naive question. I'm not understanding how HTO H2O is still in the atmosphere at 65 degrees Kelvin. I'm deciding why I think this.
Yeah, so question about why water is still in the atmospheres of, for example, 75 Kelvin objects. For these cases, they're all like iced out, like you said, water ice cloud. They all condense out in the atmosphere. So you see and follow the abundances of these objects. They will condense following the saturation vapor pressure of expected chemistry of water in that case, and it will rain out in that case. And then, but you might not see it, for example, for those colder objects. So you have like other cloud decks further on, like ammonia clouds further up, or even methane clouds above it that might be covering the water cloud, for example.
Right, well, let's give another round of applause.
Hi, everyone. My name is Hannah Voss. I'm a student at Christian College Dublin. It's my immense pleasure to be your chair for the final two talks of today's session. That topic very close to my heart, and that is